Every device on the internet has an address. Not a street address, not a name. A number. And that number is how every message, every video stream, every search result finds its way back to you. That number is called an IP address. Understanding how it works unlocks something fundamental about how the entire internet is built. So what exactly is an IP address? Where does it come from, and who decides what number your device gets? Let's start at the very beginning. IP stands for Internet Protocol. It is the foundational rule set that governs how data moves across networks. Every device that participates in a network, your phone, your laptop, a web server in a data center, a printer in an office, a smart thermostat on your wall, needs an address. Without addresses, there is no way to route data from one place to another. An IP address is that address. It is a unique numerical label assigned to a device so that other devices know where to send information. Think of it like a postal address, but for packets of data flying across a global network at the speed of light. Without it, the internet does not know where to deliver anything. There are currently two versions of IP addresses in widespread use: IPv4 and IPv6. IPv4 came first. It uses a 32-bit number written as 4 groups of digits separated by dots. Something like 192, 168, 1, 1 or 203, 0, 11345. Each group can range from 0 to 255, giving us roughly 4 billion possible unique addresses across the entire planet. 4 billion sounds like a lot. In 1981, when IPv4 was standardized, it seemed more than enough. The internet was an academic experiment connecting universities and research labs. Nobody anticipated that billions of people would each carry multiple network devices in their pockets within a few decades. The internet ran out of IPv4 addresses, not metaphorically. It literally exhausted the pool. The last block of unallocated IPv4 addresses was distributed by the Global Registry in 2011. The internet has been running on creative workarounds ever since, rationing and recycling addresses in ways the original designers never intended. That is where IPv6 comes in. IPv6 uses 128 bits instead of 32. It is written as 8 groups of 4 hexadecimal digits, separated by colons. The address space it creates is almost incomprehensibly large. We could assign a unique IPv6 address to every atom on the surface of the Earth and still have addresses left over. The shortage problem is permanently and definitively solved. Both systems are running simultaneously right now, all over the internet. Your device almost certainly has both kinds of addresses depending on which network and which service it is connecting to. The industry is slowly migrating, but IPv4 will be with us for many years yet. Now let's talk about where these addresses actually come from, who hands them out, and how does the system stay organized. At the very top of the hierarchy sits an organization called IANA, the Internet Assigned Numbers Authority. IANA is a function operated by ICANN, the Internet Corporation for Assigned Names and Numbers. IANA is the global steward of the entire IP address space. It does not assign addresses directly to you or your company. Instead, it carves a total address space into large blocks and allocates those blocks to 5 regional registries spread across the globe. These 5 organizations are called RIRs, Regional Internet Registries. ARIN covers North America. RIPE-NCC covers Europe, the Middle East, and Central Asia. APENIC covers the Asia-Pacific region. LACNIC covers Latin America and the Caribbean. And AFRINIC covers Africa. Each RIR is a non-profit membership organization responsible for fair and efficient allocation within its region. Each RIR then allocates smaller blocks of addresses to internet service providers, large enterprises, universities, government bodies, and cloud companies operating in their territory. The blocks get smaller as they travel down the chain, from millions of addresses at the RIR level to thousands at the ISP level to individual addresses reaching your home. Your internet service provider, your ISP, is where the chain finally reaches you. The ISP receives a large block of addresses from the regional registry. When you connect your home router, the ISP assigns one of those addresses to you. That address is what the rest of the internet sees whenever you send a request anywhere in the world. There are 2 ways an ISP can assign that address, dynamic or static. Dynamic means the address can change. Every time your router reconnects, or periodically by the ISP's own scheduling system, you may receive a different IP address drawn from the pool the ISP manages. This is the most common arrangement for home internet connections, and most users never notice or care. Static means the address stays the same every time. Businesses that host their own servers often pay for static addresses so that their clients can always reach them at a consistent, predictable location. Static addresses cost more and require deliberate management, but they are essential for anything that needs to be reliably findable day after day. Now here is something important about how your home network is actually structured. The address your ISP gives your router. That is your public IP address. It is the address visible to the outside world. But inside your home, your router runs its own separate private network. Every device on your Wi-Fi, your phone, your laptop, your tablet, your smart TV, gets its own private IP address assigned by the router. These private addresses fall within reserved ranges like 192.168. XX or 10. XXX, they're invisible to the internet. Nothing outside your home can reach them directly. Your router manages the boundary between these two worlds using a technique called NAT, Network Address Translation. When your laptop sends a request, NAT replaces the private source address with the router's public address and keeps a record of which internal device made that request. When the response comes back from the internet, NAT routes it to the right device on your private network. Billions of devices share the public internet through this mechanism every single second. NAT is a big part of why IPv4 survived as long as it did. It allowed thousands of devices to share a single public address rather than consuming one each. But NAT adds complexity, breaks certain protocols, and introduces latency overhead. IPv6 is explicitly designed to make NAT unnecessary. Every device can have a genuine globally routable address of its own. There's one more layer worth understanding: how your device gets its address automatically when it joins any network. When you connect to a Wi-Fi router or plug into a corporate network, your device does not already know what address to use. It broadcasts a request asking for configuration, a service running on the router called DHCP, the Dynamic Host Configuration Protocol, responds within milliseconds. It hands your device an IP address, a subnet mask defining the local network, a gateway address for reaching the outside world, and the addresses of DNS servers for resolving names. Your device applies all of this instantly, and you're online. DHCP is why connecting to any network feels completely effortless. The hotel Wi-Fi, the coffee shop hotspot, your phone's mobile data connection. Every one of them runs DHCP behind the scenes. You tap connect, and the entire address negotiation happens automatically before you are even aware it has occurred. Now let's talk about what an IP address actually reveals, and what it does not, because it genuinely matters. Your IP address exposes your approximate geographic location, typically down to the city or region level. It identifies your ISP. Every server you connect to can log it. This is normal and necessary for the internet to function. But an IP address does not reveal your exact street address. It does not contain your legal name. It is a network location, not a personal identifier on its own. However, your ISP maintains detailed records of which customer account was assigned which IP address at every moment in time. So while a random website cannot identify you from an IP address alone, your ISP absolutely can. And by extension, so can law enforcement given a valid legal request and ISP cooperation. The privacy implications are real and worth understanding. This is exactly the mechanism that privacy tools like VPNs exploit. A VPN routes your traffic through a server operated by the VPN provider, which has its own public IP address. The website you visit sees the VPN server's address, not yours. Your ISP sees that you are connected to a VPN but cannot inspect the content of what you are doing. The trade-off simply shifts. Instead of trusting your ISP, you are now trusting the VPN provider's logging policies and jurisdiction. Understanding IP addresses is not just interesting trivia. It is the bedrock for understanding routing, firewalls, DNS, load balancers, cloud infrastructure, containerization, and virtually every other concept in modern network architecture. Every single time data moves from one place to another, across any network, anywhere in the world, IP addresses are doing the fundamental work of labeling source and destination. The internet is a postal system operating at unimaginable scale. Hundreds of billions of packets per second, each one carrying a source address and a destination address, each one finding its way through a web of interconnected networks spanning the entire planet. IP addresses are the labels. The registries are the postmasters. And the protocols are the agreed rules that make all of it work, reliably around the clock for everyone. That is IP addressing. Thanks for watching.